put big injectors in your Polaris, your Turbo R Pro XP, either because you've cranked up the boost considerably from stock, or you've converted to ethanol, or even better, methanol. It's a pretty simple upgrade. I mean, the mechanical part you guys can all handle. Let's look at how you handle the calibration aspect. So the first thing you're going to do is navigate to the Injector Dynamics website, which is injectordynamics.com. Not too hard. Let's see, you scroll down to UTV products, specifically go to Polaris, and scroll down a ways. You'll see a couple of data generators, one for a Pro R, one for a not a Pro R. It's not too hard to figure out. Click on that. Hope my internet connection is good. Well, I did say hope, didn't I? Does this get better? Yeah, okay, not too bad. All right, let's go. So first of all, let's say, well, ethanol. You want 1300s. You need to enter the engine displacement. Of course, the displacement of those two vehicles that I mentioned is 925 cc's. You can change that value if you have stroker crank or overbore. Now you can change these values with a slider or with the plus and minus buttons, but these things are really not that useful. They're just an artifact of the software that we use to build this generator. Just enter the number. It's a whole lot easier. You don't have to fiddle with it. Tell it how many cylinders you have, in this case 2. Now it knows the displacement per cylinder. And aspiration, well, it's not naturally aspirated. It's not an RS1 or an XP1000, so let's switch to forced induction. And pressure reference. The question there is the pressure regulator reference to the atmosphere or to the intake manifold? So let's assume that you did the right thing for a turbocharged vehicle, which was to convert to a returnless map reference system. So click on intake manifold, and our standard return style system is 3 bar, which is 43.5 psi. Enter that. Note that if you're converting to methanol and you're running, let's say, to the maximum limit of the stock turbo, which is going to put you at about 250 to 260 kPa, you would probably run the 4 bar system, which is 58 psi, but that's not the case here. We'll stick with ethanol. Let's do X85 from VP. So by the time we get down here, we have to choose what fuel we want, and the reason for that is that the injector flow rate that the ECU needs to see is mass-based, and it also needs to know what the stoichiometric air-fuel ratio is. And if you don't know what that is, look it up. I'm not going to cover it in this video. So your first choice here is gasoline or ethanol. Now, pump gas typically is 10% ethanol, maybe as high as 15, depending on where you live. I would like to think that you're not racing on pump gas, but if you are, that's the option, 10%. If you're running, let's say, VP X85, which is 85% ethanol, you'd simply enter 85. If you were running methanol, just click methanol. That's not too hard. Now, let's say that you're racing in a class that doesn't allow any alcohol. I hope that's not the case, but maybe it is, or maybe you're running gasoline for, whatever reason, or something you batched up in your backyard. I don't care. Click on custom fuel. Now, once you click on custom fuel, the ethanol content, of course, doesn't matter, but the stoichiometric air-fuel ratio does. So let's say you're a complete lunatic and you want to run nitromethane. There you go, stoic of 1.7, and along those same lines, density of 1.14. Well, I mean, if you want to try it, go ahead. It's probably not going to run very long, but let's choose some more reasonable values. VPMS 109, I think stoic is about 13.6. I'm going from memory, doesn't matter, just want to show you some values. Density is 0.745, I think. And we're done with all of this input. At this point, it generates all the values up here in blue, which are the values that we need to paste into the software. Now, we have one left, which is the injector pulse width axis breakpoints. We'll get to that in a bit. For now, let's just switch back to a gasoline ethanol mix set to 85, because we've decided we're going to use VP X85 and get to work. So you open up your file on HP Tuners, click on Engine, Fuel, it's already there. It's almost like I planned this, huh? The injector slope, I think, has been changed as well. No, that's probably stock. Okay, so let's go back. Double click on this. This is your new injector slope. Right click to copy. Come back into HP Tuners, same thing, double click to select it. Right click, paste. Alternately, you can use Control V and Control C on the keyboard, whatever works. So we've just defined the injector flow rate, or the injector slope, in terms of mass flow. So now let's move on to the injector constant multiplier. So the stock fuel system is not map referenced, and so the differential pressure across the injector changes with boost or manifold vacuum, and this table is there to account for that. And so what will happen is, if the fuel pressure was really low, like say 14.5 psi, which would be ridiculous, it knows that it needs 93.8% more fuel. This is an important feature of the ECU. If this were naturally aspirated, it would be very important. Turbocharged, it's still important. However, when we convert to a return style map reference system, you're going to see that this is not critical. And we have a video about that I did just recently. I think you should go check out. It explains the intent of the map reference return style system. You know what? Let me just go there. Let's see here. Let's go to a new tab. Go to YouTube, and we're going to go to Injector Dynamics TV. Let's see what we get. Yep, that's us. And just so you know, this YouTube page is really old. We don't do much with it. We never have. We're an engineering company, not a marketing company. But we are making an effort currently to get some more information up here. When I say information, I mean just that, not fluff, real information. So here's the video here. It's up on top under the UTV Fuel Delivery Tech videos, of which there's currently one. Of course, there'll be another one here shortly, and I continue to work on this. But watch this video. It explains the purpose of the return style system, why you really should be converting to this system if you have a turbocharged vehicle. So now that I've got that out of the way, let's go back to the calculator and our injector constant multiplier. I'm going to grab these values as if we were not referenced to the intake manifold, if it was still referenced to atmosphere. I'm going to copy those, go back here in the software, and we have to change these breakpoints. Now in HP Tuners, you simply click on the axis label, left click on the first cell, drag it across, it selects all of them. You can either Control V for paste or right click for paste. Boom, values are changed. Now you can close that window out, and whoops, made a mistake there. Okay, so these values have changed. We still need to enter the actual values that matter. So let's go back here. Whoops, back here. And you'll notice these are all ones, and the reason they're all ones is that, well, the differential pressure across the injector does not change, which is the whole point of the map reference return style system. If we were still referenced to atmosphere, which I hope you're not, click that and wait for it to update. You'll see these values change. I'm going to go back to the proper system. We'll select these, copy, and same thing, paste. Alright, that's done. Now we need to get to the pulse width minimum, or the minimum pulse width. So here's what this is about. Every fuel injector has a minimum pulse width below which the output becomes very erratic. And so by setting a minimum, it keeps the it keeps the ECU from delivering a pulse width below that, and that often results in a mixture that's overly rich. However, that's better than erratic fuel flow, and so that's why this this value exists. So let's grab this. Whoops, should click on the right damn button first. Copy that, paste it in. That's done. Now we go to the injector voltage offset. And we have to change this axis. We're going to change this to 8, 10, 12, 14, and 16. Easiest way to do it is just select it. Same thing, copy. Back here. This time I'm going to Control V. Same thing, same end result. And now we need to put the table values in. So we'll go back and grab those. All 5 of them. Copy. Now, by the way, I mentioned you can click one cell and drag across to select them all. Now, the other thing you can do in HP Tuners is just click up in this corner cell. It selects them all. I'm going to right click, paste. Boom. Those are updated. Believe it or not, we're almost done with our injector conversion. Now, this is a little more complicated. And it's still copy and paste. And if you can't copy and paste, you probably shouldn't be tuning cars. In fact, I should add that to a long list of things that should disqualify you from tuning cars, but I'll save that for another video. So one of the things we have to do here is count the number of breakpoints. Now, remember I said before that this was something we would get to later. Well, let me show you what this is all about. When we did this calculator or data generator initially, we noticed there were 16 breakpoints in everything that we looked at. We don't have a stock file for everything. We don't know what they might come out with next year. Maybe there's a 5-year-old car we haven't seen that has 14 breakpoints or 15 or 21. So we made that a variable so that we can generate the appropriate range of pulse widths. So I'm not going to count that because I know it's 16, but I want you to count it. Go back here, make sure the right number is entered, which it is. In fact, I'll show you what happens here if I change it. See, there now I've got 21 breakpoints, and they are scaled exponentially from the minimum pulse width up to the maximum pulse width that you could expect to see on any of these engines. So I'll change that back to 16. Hope the table updates quickly. It does. Okay, now the other thing is that so far we've been selecting multiple values without issue, but we noticed that when we presented a full 3D table, in some instances with some browsers, when we would select all of these values, some really screwy things would happen when we tried to paste after copying. So we just gave you a button that handles that and converts these to a format that HP Tuners and DynoJet are happy to accept. So let's copy the pulse width axis, which is this. Copy that. Come over here. We will select the axis. All right. And we'll select all these values. Control V, or right click and paste. That's done. And now we have to fill in the table values. So we'll go back here and we'll click on Copy 3D Table, which copies all of these values and converts them to a format that's going to paste properly. And we can either grab one corner and drag to select all of the cells, or we can just click this top corner, selects all of them, right click, paste. There we go. So click on the visual. You can see what's going on here. Essentially what's happening is as the ECU is commanding lower and lower pulse widths outside of the linear operating range, it's pulling fuel out. And whoops, I didn't mean to do that. Ah, there we go. That's the value I wanted to see. So let's say, for instance, that the computer decides we need a injector pulse width of 0.69 milliseconds to deliver the appropriate amount of fuel. Well, what's going to happen here is it's now going to multiply that value by 0.906. And the reason is that this particular injector at that fuel pressure runs about 10% rich at that pulse width. And so this makes the correction so that the air-fuel ratio ends up being what it's supposed to be. Now, without this nonlinearity compensation in this table, what will happen is you flash the injector data into the ECU, your offsets and your slopes, and it would be approximately 10% rich under these conditions. And so in most cases, you would go to the speed density section or the airflow section into your VE surface, and you would fudge these values down here to get the correct air-fuel ratio. The problem is that that's not the correct way to do it. You're really screwing up the air model when in fact it's the fuel model that needs to be changed. So this is the correct way to do it. And this is, of course, one of the benefits of buying a quality injector from a company that knows what the hell they're doing. So there we go. We've got this table done. I'm actually just going to copy this since it's the same for cylinder number 2. Paste it into there, and we'll do a quick visual. Yeah, looks sort of the same, but not exactly. The reason is that I have not changed the pulse width axis. So we'll go back and do that again. Copy the pulse width axis. Hope I'm not jumping around too much. Paste that, Control V. Now we have the same curve here, the same breakpoints as we did in cylinder number 1, and you'll notice that the visual now looks the same as cylinder number 1. So there we go. We've taken care of our injector linearity or our non-linearity compensation, so that we can expect, without any other changes, the values to be correct. And having done all this, we've basically covered the fuel portion of the model. And what's important to understand is that this is a model-based system. You have an air model, which essentially tells the ECU how much airflow will the engine, or how much air will flow through the engine under any given condition. And then this model describes what the injectors do under various combinations of fuel pressure and pulse widths. Knowing those two things, it looks up what the air-fuel ratio should be in a table, and it can quickly calculate the appropriate air, quickly calculate the pulse width required to give the correct air-fuel ratio. And when you get this stuff correct, you could, let's just make a really extreme example, because I've done this. That's part of what we do here in our testing and validation. You could grab a Turbo R from your dealer, bring it back home to your shop, your garage, whatever, pump the tank, fill it with methanol, which is obviously very different from pump gas. Use the calculator to tell it I've got 1300s in it. I've converted to a map style, map reference return style system. You know, install the new rail, the regulator, the fuel lines. Get that all done. Hit the key. The car will start. The air-fuel ratios will be, well, in this car they'll be spot on because it runs in closed loop all the time. But you'll find that your trims will be, you know, plus or minus a few percent, maybe plus or minus 5% tops. But the point is, after doing this, you plug the data in, you can go out and rage the vehicle around, run it on the dyno to do some fine tuning. It's not the situation you may be accustomed to, where you change to a bigger injector and then you come in here and you fudge these values to the best of your ability until the car runs, sort of. And typically what happens in those instances is that your tuner doesn't want to spend a week on your car. He wants to spend, you know, a day or 2 hours or 3 hours, and he gets it making the power that it should on the dyno, but all of the other stuff is screwed up. The car doesn't start well, transient fueling is a mess, air-fuel ratios are way off at idle and cruise. So in this case, by having the correct data and putting the correct data into the ECU, you've essentially made a change that the model in the ECU can account for, and everything works pretty much as it did before. And it's really that simple and that quick. So we have to consider one more thing here, and I hope I don't screw this up because this is relatively new. HP Tuners just added this for me. I've got to do it from memory, and I haven't looked at it in a few weeks, but allow me to explain. The Turbo R and the Pro XP have a fuel pressure sensor. It's the only UTV on the market that does, and it has a fuel pressure target that is controlled by the ECU, and it controls that by varying the speed of the pump through pulse width modulation. So it's always trying to hit a specific target, and the fuel pressure sensor is there to make sure that it's hitting its target. And if it goes outside of that target by more than a relatively small margin, it throws an error and it doesn't allow you to get full throttle because it senses that something's wrong with the system. This is one of the dreaded limp home Polaris modes that many of you are familiar with. And to be clear, it's not the fault of the computer or the car. The problem is that you've screwed up its model, right? It knows how things are supposed to be done, and basically you've screwed it up. It's like you've gone to its desk and just rearranged everything. So we have to account for that. Now, by the way, you don't have to do this on a Turbo S. This is specific to the Pro XP and the Turbo R. So, man, I said I was going to do this from memory, didn't I? Well, it's all from memory, but as I said, this is new. And by the way, thanks for HP Tuners for getting that added. Maybe I said that already. Let's go to the fuel system. Um, let's see. Here's the desired set point from the factory. So without making any changes, the system is always going to try to provide this fuel pressure under these conditions. Now, we don't want it to do that because we have a mechanical regulator that's now controlling pressure. We don't have to change this. It doesn't matter what it is. We're going to tell the computer, the ECU, to ignore it. So we're going to go to the fuel pump settings, and the first thing we're going to do is change this table, which is the feed forward table that says, hey, under these conditions of mass flow and desired fuel pressure, this is what the duty cycle to the pump should be. So we're going to change these to all 50s, which is going to make the pump run at 100% all the time. Now, it's important to point out that 50% in this table means 100% duty cycle at the pump. I don't know why, but that's how it is. Raising this value higher does absolutely nothing for you. So again, the pump is now going to be running basically at full blast all the time, and the mechanical regulator on the end of our fuel rail, on our return style system, will be controlling pressure. Now, the other thing is that we have to tell it to stop making corrections. That feed forward table gives it a starting point. It says, aha, under these conditions give me 32% duty cycle. But then it fine tunes it to get the exact pressure. And these parameters control that fine tuning. These parameters are part of what's called a PID loop, or in this case, a PI loop, just proportional and integral. So we're going to zero these out. And as soon as we do this, the ECU is going to stop correcting. It's just going to put zeros in here. Okay, so now it's no longer making corrections. It's only going to deliver this duty cycle to the pump at all times. And again, fuel pressure remains constant at 3 or 4 bar differential because our mechanical regulator is now getting the job done. So let's see, is that all that I needed to do? Oh, battery multiplier. We want to set these to all ones. So regardless of battery voltage, it's going to take the number in this table, which is 50%, which gives us 100% at the pump, multiply it by 1. So it's always 50%, and it will not be making any corrections no matter what the fuel pressure is. And I think there's one more thing that I'm forgetting. What the hell? Oh, I remember. We have to tell it to stop getting angry. Engine diagnostics. Okay. Yeah, here we go. Under general and fuel pressure, this is the maximum allowable deviation from the target fuel pressure. And the fuel pressure that's set with the mechanical regulator is not at all what's in the table. And the table does not have the appropriate axes to allow us to define it. So basically, we're just going to blow these values out so that it never passes that threshold. So we're going to change -40 to say -500 kPa, which is 72.5 psi below target. In this case, we'll change it to 500. That's 72 psi above target. And now we don't have to worry that it's going to get angry and pull the throttle and go into limp home mode because the fuel pressure that the fuel pressure sensor is reading is always going to be within this threshold, so it won't get mad at you. And here we are. Let's see, how many minutes are we into this? 24, that can't be correct. Well, I got through it quickly, I think, in one take. I'll go back and look the video and see if I need to edit anything, but that's it. It's really that simple. So buy the parts, put them on, change the fuel, plug it in, and this thing will run far better than you ever would have expected. That's it. Thanks.